Okay, welcome back, everybody. At the end of lecture yesterday, I had stated Taylor's theorem and said a couple things about it, but now I wanted to talk a little bit more about it. Here's the statement of Taylor's theorem back on the screen. So suppose that you have an analytic function throughout some disk centered at z0 of radius, say r0. And so in particular, this thing is analytic at z0, right? Since the disk itself provides the neighborhood that it's analytic on. So we have a function analytic at the point z0 on this disk, or I should just say analytic at z0, but it's analytic throughout this disk. Then f has power series representation given by this expression. That is, it is a sum from n equals 0 to infinity of a sub n times z minus z0 to the n on this disk, okay, where the coefficients in this power series are the familiar coefficients coming from Taylor's theorem in Calc 2, okay? And so another way of saying this is saying that the series defined in this way, so forget that I have f of z here, the series defined in this way converges to my function f of z when z is in this open disk. Okay. All right. And so finally, this gives us the statement that I had mentioned before. So this means, in particular, f analytic at z0, this implies that f has a power series expansion around z0, or about z0. Having a power series expansion around z0 is exactly that statement, the consequence of Taylor's theorem. Of course, this is going to go in both directions. Okay, and so if we wanted to, we could have actually defined this word analytic to mean has a power series expansion around the point. So we could have defined analytic at a point to be has a power series expansion around that point. In fact, that is the typical definition of analytic. So if you've seen the word analytic coming from real analysis, that is how the word analytic is defined there. So in this course, we began by using so for us, when we said f is, we'll say complex differentiable, at z0, as I mentioned to you before, to say that this is complex differentiable, that it had a complex derivative at the point z0, and to make our lives easier, we'll say that what we mean by this is that it has this complex derivative not just at z0, but in some neighborhood of z0. Okay, that in that case, there were many words we could use to describe this. So in this course, we use the word analytic. Okay, but we didn't need to do this. If we didn't do this, okay, if we didn't use this word analytic and we saved it, held it back, and used it only for this case, all right, then maybe another word we could have used, and this is something that you'll commonly see if you're looking up complex things here, is rather than saying analytic here, you would say holomorphic at z0. So holomorphic means has a complex derivative at z0, and a holomorphic function then would replace the term analytic that we've used, and nothing would change here. All those theorems about analyticity that we had before, we would just replace the word analytic with holomorphic. And if we had done that, right, going all the way through to here, this statement would be f is holomorphic at z0 if and only if f has a power series expansion around z0, and we could define having a power series expansion around z0 to be analytic. And so this Taylor's theorem is the statement that a holomorphic function is analytic. Okay, could have done it that way, but the thing that's so awesome about complex analysis is that holomorphic and analytic, they're the same thing. All these things, all these notions are the same, right? And having, say, one complex derivative, right, it tells you that you have them all because your derivative itself is also analytic or holomorphic or whatever. And so finally, this is the thing that we get. I said at the very beginning that this is going to turn out to be the case, and this is the usual definition of analytic. But now we don't have to worry about any of that. When we say analytic, we get all of the stuff that we expect to get here. Okay, now why is this so nice? So this is nice for a variety of reasons. It's nice for all of the same reasons it was nice in calculus, right? So this is nice for all the same reasons it was previously nice. So in Calc 2. So namely, a power series is a sort of infinite polynomial. And thus, if we have a power series expansion for some function f of z, it enables us to do all sorts of convenient, we'll say, computations. Okay, but I don't want to imply that this is only a computational thing that's nice for. This is nice for a variety of reasons. Sometimes with the power series expansion, you can just see various properties of this function. So, for instance, you could see, that like in Calc 2, right? You can see directly from the power series definition, or from the power series expansion, that like sine of x is an odd function, or cosine of x is an even function. If you have the power series expansion for those things, you can just see that's a property of these things. Okay, so what else should I say here? So first of all, the proof of Taylor's theorem I'm going to skip. Proof of Taylor's theorem is always a little disappointing in that it's a proof that kind of just works. This is true when you talked about Taylor's theorem in Calc 2 as well. But I'm not really going to say anything more about it. If you're interested in the proof, this is done in at an entire section here that starts on page 190 in the textbook. The difference between this proof and the other one is this is going to use the Cauchy integral formula. So this relies on Cauchy integral formula, which is why it had to wait until now, right? Until we had this at our disposal. Okay, so if we have, let's say that we have an analytic f at z0. So if f of z is analytic at z0, then it's got a Taylor series expansion about that point. So it is equal to the sum from n equals 0 to infinity of the nth derivative of f at z0 over n factorial times z minus z0 to the n, right? And this is for z belonging to this this ball, right? Centered at z0. Okay. Okay. So recall, so this thing is called the Taylor series when it's written in this form. Recall that, for instance, 0 factorial is defined to be 1, and the 0th derivative of f at some point is actually just the value of f at that point. Okay. Then, writing this out, this means that f of z can be written as f at z0, so f of z0, that's the 0th term, plus f prime of z0 over 1 factorial times z minus z0, plus f double prime of z0 over 2 factorial times z minus z0 squared, plus f triple prime at z0 over 3 factorial times z minus z0 cubed, and so on, right? So that's what this thing looks like. Okay, and this is, of course, for all z belonging to this neighborhood. This is what it means to expand f as a Taylor series about z0. Okay. All right. And so if f is analytic about z0, it has a Taylor series about z0. Okay. And what this means then is that, note, if f is entire, that is, it is analytic on the entire complex plane, R0 can be chosen arbitrarily large. Okay. I.e., this condition becomes, so this thing becomes all z such that the modulus of z minus z0 is strictly less than infinity, i.e., you know, f of z, or I should say the Taylor series, converges to f of z for all z, right? And so in this case, right, you have that Taylor series being an expansion, or your function having a Taylor series expansion about, you know, any point in the plane, and you could, you know, you could use any Taylor series expansion that you want to, right? So this z0 Could be anything. Okay. All right. So what else to say here? All right, being careful with the terminology. Suppose, so that's if we went through the case of if f is analytic at a point, it's got this Taylor series expansion about that point, right? And this holds for z within some radius r naught of that point z naught. If it's entire, then I have this on the entire complex plane. Okay. Now, what if I have a function that's analytic, say, everywhere inside some circle centered at z naught? Okay. So when f is analytic at every point in some circle, so when f of z is analytic at every point in some circle centered at z naught, convergence of its Taylor series about z naught to f of z is guaranteed. And by Taylor's theorem, actually, we don't even need to check. There's no kind of convergence test that we even need to do. So no convergence test needed here. So this is nice. Okay, I get that automatically. Okay, this is directly from Taylor's theorem. Okay, so to see this by Taylor's theorem, another characterization of what it is that's going on here is the following. The series, that Taylor series that I wrote down, converges to f of z within the circle about z naught, whose radius is the distance from z naught to the nearest point at which f fails to be analytic. Okay. So the series f of z, so the series converges to f of z within the circle about z naught, whose radius is the distance from z naught to the nearest point z sub 1 at which f fails to be analytic. So this underlined portion is a nice way of characterizing what this statement of Taylor's theorem says. Okay. It turns out that this is maximal. Okay, so this is the largest such circle. Okay. So if you like, this allows you to fill out, your plane with, the largest circles possible on which f has, or on which this a given expansion about a point z naught it converges to f of z. Okay. So even though I'm not going to do the proof, the way that the proof goes is similar in spirit to the way that it goes in Calc 2, which is that first you actually show it for an expansion about 0. Okay, so idea of the proof. First show it for the Taylor series expansion about z equals 0, or z naught equals 0. But the Taylor series expansion about z not equals 0 is something that is important enough, that is, it comes up enough to actually have its own name. So that is, I want to show that f of z has, the following Taylor series expansion. So this is the sum from equals 0 to infinity of the nth derivative of f at 0 over n factorial times z to the n, right? And this is for modulus of z strictly less than r naught. This particular type of Taylor series, that is the expansion about z not equals 0, is called a Maclaurin series. So this is called a Maclaurin series. Okay. Once you show Taylor's theorem for a Maclaurin series instead of a Taylor series, the actual general case follows pretty much immediately as a consequence of this. Okay. And so I wanted to mention this because using the Maclaurin series instead, for instance, for say like some entire function like e to the z, that's typically like the first thing you want to look at here, allows us to quickly compute some of these Taylor series expansions for familiar functions. Okay. All right. And so what do we know? Well, first of all, I'm not going to state it yet, but it turns out that if, in general, we have a function that is equal to a power series, okay, for all z interior to some circle centered at z naught, if this is true, then actually this series must be the Taylor series. So there's a uniqueness of these power series expansions. Okay. And so this can let us, using this fact, can let us actually compute these coefficients in a way that can be easier than doing it in Taylor's theorem. Okay. And so what we can do is that we can actually use, say, the Maclaurin series expansion to find certain power series representations for some nice entire functions. And then we can use some basic algebra involving power series to actually come up with power series expansions for slightly more complicated functions. So let's see examples of that. So, and the key thing here is that we can actually find, say, Taylor series expansions in maybe a more convenient way by taking advantage of this fact, because it actually doesn't matter how these coefficients arose. If we can actually find a power series expansion for which this is the case, then we're happy. Okay, and so let's do a couple of examples here. So here's first example. Let f of z be e to the z. Right? This is entire. Okay, and so I don't have to worry about a window, right? I don't have to worry about some neighborhood where this thing has a power series expansion. I can apply Taylor's theorem. Since this is entire, I can use any point I want to. So I'm going to use the Maclaurin series, right? I'm going to do z not equals 0. So let z naught equals 0, its Maclaurin series is valid for all z, right? Valid for all z in the complex plane. Or what is its Maclaurin series? Well, this is easy enough. Note the nth derivative of f is e to the z, right? Okay, so that's easy enough. Thus, the nth derivative of 0 is e to the 0, which is 1. And this is true for all n, right? So for all natural numbers n, nth derivative of f is e to the z, so evaluating that at 0, this is just always 1, okay? And so the Maclaurin series for this function e to the z is, writing this out, this is the sum from n equals 0 to infinity of the nth derivative of f at 0 over n factorial times z to the n. So rewriting this, this is the sum from n equals 0 to infinity of z to the n over n factorial. Okay. But of course, f is e to the z, so this is just me saying that e to the z has this power series expansion. Okay, and this is true, you know, if you absolutely must write the window, this is true for modulus of z less than infinity, i.e. all z in the complex plane here, right? Okay. Well, note that from this you can actually deduce the usual expansion for the reals, right? So if you let z actually just be the real number x, then this expansion is going to be the familiar one. E to the x is the sum from n equals 0 to infinity of x to the n over n factorial, right? Where modulus of z is less than infinity is going to mean that x is going to be between minus infinity and infinity, right? So it's just any real number. That's the usual Maclaurin series for e to the x. Okay. All right. Now, this boxed term in some complex analysis textbooks, so for instance, if you take graduate complex analysis at UMD, I believe they still probably use Serge Lang's complex analysis text, at least they did when I took it, and like first thing when e to the x is mentioned, or sorry, e to the z is mentioned, is it is defined to be this. Okay, so actually, e to the z is actually defined using the power series in that textbook, and I've seen that done in other textbooks too. And then from this, you know, from this definition, all the other all the other properties that you're familiar with of e to the z now are derived. But of course, we don't have to do it that way, and that's why you can define it this way, is because we could have started just as we did, right, with another definition of e to the z, and we arrive at this by Taylor's theorem. Okay, you can do the same thing for sine and cosine here, and then we'll see that in just a second. Okay, now what if how can I use that to give, say, a quick power series expansion for some other function? Okay, well, what about if I have the function z squared times e to the 3z, right? Well, what I do is I go back to my expansion for e to the z. To get e to the 3z out of this, of course, I can just replace z with 3z in this expansion. Okay. And then to get the power series expansion for this thing, I just multiply through this power series by z squared, which I can just think of doing that term by term, and I can see exactly what's going to happen here. Okay, if you like, I'm shifting my coefficients, right, in the power series expansion. Okay, and so the easiest way to do this is exactly that way I described. And so the power series expansion that I'm looking for z squared e to the 3z, this is also entire. So I don't have to worry about what point I choose here. I can use the Maclaurin series perfectly fine. So then what does the power series expansion for this thing become? This is the sum from n equals 0 to infinity of, so I've plugged in 3z here. Out from that, of course, pops a 3 to the n. Okay, multiplying by z squared shifts my powers of z right up by 2. And so this is actually 3 to the n over n factorial, z to the n plus 2. Right, and so the lowest power of z showing up here happens in the 0th term, and that's z squared, right? That makes sense. Okay. All right. So, of course, another way of writing this, right? Another way of writing this, if you wanted to shift this in such a way that you shift your indices, another perfectly valid way of expressing this is writing this as the sum from n equals 2 to infinity of, now I have to shift the indices to make up for the fact that I'm starting at n equals 2 here. So if I'm going to start at z to the n, so that my first term here has power z squared, right, then I need 3 to be raised to the power n minus 2, right, so that these match up term by term. And I need this factorial term to start at n minus 2, right, factorial. So z to the n. Okay. So of course I can always rescale this so that my power of z here is n. But of course no reason to do that unless you just really want to. And this is of course for z in the complex plane. Okay. Now, what is the thing I'm trying to get across here? It's that these coefficients, notice these coefficients here or here, while it's true that this ends up being the same as the Taylor series expansion, notice that I didn't actually have to use the formula coming from Taylor's theorem to actually compute these, right? I was able to compute them in another way, just doing some basic algebra. Okay, and using previously found expansions. All right, so that's the idea. So let's do another example. So let's let f of z be equal to sine of z. Okay. Now, recall that the definition of sine z that we gave, right, and the one we've been using this whole time, is this is e to the iz minus e to the minus iz over 2i. All right, so this is our definition of sine of z. Okay. So I want to find the Maclaurin series for this thing. Okay, but in order to do this, rather than actually computing here, I'm going to do this from my Maclaurin series expansion for e to the z. Okay. So what do I do here? So I say that sine of z, right, using this, this is 1 over 2i times e to the iz, that is really the sum from n equals 0 to infinity of I z to the n over n factorial. Okay, minus the sum from n equals 0 to infinity of minus iz to the n over n factorial. Now, you might stop here and say, wait, do I have to do it this way, or can I actually just use Taylor's theorem? Because sine of z is something that's pretty easy to compute derivatives of. And so can I just use Taylor's theorem and the fact that I can compute these derivatives. I have this cyclic derivative, right? So if you compute derivative of sine z over and over and over again, you'll notice pattern, and then you can try to adapt, that pattern to what's going on here. Yeah, you could absolutely do it that way, right? And that's probably the first way that you saw this derivation happen in Calc 2 was exactly that. In fact, in Calc 2, this might have also been like the second example you did for Taylor series. I think that's usually how I do it. So yeah, you can absolutely do it that way. But seeing it this way, we notice, oh, well, this is actually pretty easy to compute this way because this is 1 over 2i that's outside of those sums. And when I sum these things, I know that both of these sums converge everywhere because they're power series representations for e to the iz and e to the minus iz respectively. Both of those things converge everywhere, right? These are both entire functions. So I don't have to worry about convergence here. And so doing this series subtraction is not ill-defined. I'm perfectly happy to do this. So when I do that, what do I get here? The fact that I have 1 to the n here, you don't even see that, and I have minus 1, say, to the n here, this is really 1 minus 1 to the n, right, times I to the n z to the n, all over n factorial. Okay. All right. Now, let's see here. What is 1 minus 1 to the n? There's two options here, right? So this is either equal to 0. When is it equal to 0? So it's equal to 0 if n is even. And it's equal to 2 if n is odd. Okay. So it's equal to 0 if n is even, 2 if n is odd. What about I to the n, right? What is I to the n? Well, actually, I don't need to worry about what I to the n is in general because this 1 minus 1 to the n, this is 0 if n is even. So I only have to consider odd terms here. And if I am raising I to an odd power, what do I get? Well, this is minus 1 to the n times I, right? Right, so if I begin at just the odd power 1, it's just I, and then I cubed is minus I, right? I to the 5th is I again. I to the 7th is minus I, and so on. Okay, so every other odd number, it's minus I. Okay, and for the others, it's just I. Okay, so putting all those things together, what do I get here? So this is 0 when n is even, and so only odd terms show up here. When n is odd, first of all, 1 minus 1 to the n is 2. So this thing is 2, which cancels out with the 2 in the denominator here. This expression, I to the odd power, is minus 1 to the n times I. That I cancels out with the I from the 1 over 2I. And so what I'm left with is that this is the sum from n equals 0 to infinity of minus 1 to the n, z to the 2n plus 1 over 2n plus 1 factorial. Which you might remember in maybe its more familiar form. This is when n is equal to 0, right? This is z minus z cubed over 3 factorial plus z to the 5th over 5 factorial minus z to the 7th over 7 factorial plus z to the 9th over 9 factorial, and so on. This is the usual way of writing sine of z. Okay, so now we have found a power series expansion for sine of z. This actually has to be equal to the Taylor series for sine of z, but we didn't have to compute it directly from the formula in Taylor's theorem. Okay, and of course this is valid for all z because this is entire. So we're good here. Okay. All right. Similarly, we can find the power series expansion for cosine of z. We'll see that we can also have found this doing something called term-by-term differentiation. So using term-by-term differentiation in the power series, we could have done this just as well from the previous example. But rather than doing it that way, actually, okay, sure, I will. We can find a power series expansion expansion for cosine z, but also we can find this by using term-by-term differentiation on the power series for sine z. Okay. So this is an important thing. This term-by-term differentiation, I won't get into the specifics, so specifics to follow. So specifics later. Because we'll spend a whole section doing this or saying when we can do this and showing how it works. All right. This is one of the one of the nice benefits of having a power series representation is being able to do this. To show you an example of how this works, if I compute the power series of cosine z by taking the derivative of if I say this is the derivative of sine of z, but then I use that this is the derivative of this power series that I just found, minus 1 to the n z to the 2n plus 1 over 2n plus 1 factorial. What do I mean by term differentiation? Well, it means that I can move this derivative sign inside this sum, okay, and compute it in the way that I think it would be computed here, right? So this is now you might say, wait, I know that the derivative can pull through a sum. The problem here is this is an infinite sum, right? So there's a little bit more justification that's required in order to say that we can do this. And so, like I said, I will mention specifically when we can do this and when everything works out. Here, everything is going to work out fine. So this is going to be minus 1 to the n, that's just a constant, over 2n plus 1 factorial, times the derivative with respect to z of z to the 2n plus 1. Well, I know how to differentiate that. So this is the sum from n equals 0 to infinity of minus 1 to the n times, when I take this derivative, this 2n plus 1 comes down. So this is 2n plus 1 all over 2n plus 1 factorial. Right? When I take the derivative of this thing, this is 2n plus 1 times z to the 2n plus 1 minus 1. So this is z to the 2n is left behind here. Of course, writing out 2n plus 1 factorial, this would be 2n plus 1 times 2n plus 2n minus 1 plus 2n minus 2, and so on. Writing it out as a product like that, I can cancel this 2n plus 1 in the numerator here with 2n plus 1 in the denominator, and I have left 2n factorial in the denominator. So this is the sum from n equals 0 to infinity of minus 1 to the n times z to the 2n over 2n factorial. Hey, this is actually it. This is the usual expansion for cosine z. So starting at 0 here, this is 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial minus x, or why am I writing x here? This is z. You see, I'm thinking about real analysis too much. Right, plus z to the eighth over 8 factorial, and so on. Okay, so this is this is what my power series expansion looks like. Again, this is another way of doing it without actually having to use the strict statement of Taylor's theorem to do this computation. Could I have done it that way? Yes, because again, cosine of z is a function it's easy to write nth derivatives of. Okay, this is just showing you how this can be done in another way if you're dealing with a function that is not that easy to find nth derivatives of. Okay, so let's do a few more examples. Okay, so more examples. How about sinh of z? Well, remember that sinh of z is actually just minus I sine of iz, right? Okay. This was one of those properties when we first defined these things. And so sinh of z here is following that, right, using the power series expansions I have for sine and just doing this algebra. This tells me that this is the sum from n equals 0 to infinity of z to the 2n plus 1 over 2n plus 1 factorial. Okay, and again, this is entire, so this is for all z. Similarly, since this is true for sine z or sinh z, we know that cosh z is actually just cosine of iz. So plugging iz into my power series expansion for cosine, I find that cosh z is the sum from n equals 0 to infinity of z to the 2n over 2n factorial. Okay. Okay. Note, if we want the, say, power series expansion for cosh z about, say, the point z naught, which is minus 2 pi I, right? Then what I can note is that if I want in this expression z minus z naught, which is so if I want z minus z naught to show up, this is going to be, you know, z. This is going to be z plus 2 pi I here. If I want z plus 2 pi I to show up here, well, remember that cosh of z plus 2 pi I is actually cosh of z, right? And so I could write the expansion for cosh z about minus 2 pi I in the following way from this. So cosh of z is the same thing as cosh of z plus 2 pi I. Plugging that in, this is just the sum from n equals 0 to infinity of z plus 2 pi I to the 2n over 2n factorial, for instance. Okay. All right. Now let's deal with something that's not entire. That'll be our next example. So let's find Maclaurin series, say, of a function that's not entire. So let's at the example that we actually did last time right before Taylor's theorem. We did this example of 1 over 1 minus z. Okay. Now we actually know a Maclaurin series for this. We know that this Maclaurin series is, so this is what we found, like I said, right before our proof of Taylor's theorem. This is the sum from n equals 0 to infinity of just z to the n. Now this is not valid everywhere. This is valid for z in the open unit disk, right? Okay. Now, what are my nth derivatives, right, of this thing? So my nth derivatives of this thing are n factorial. So think of computing nth derivatives of this thing. This is going to be n factorial over 1 minus c to the n plus 1. Okay. So this, notice this fails to be analytic at z equals 1. Okay, which is why this condition is important, else this doesn't make any sense. Okay. And so, notice that the nth derivative at 0 is just going to be n factorial. Okay. Right, from this. And so if we try to use Taylor's theorem here for this Maclaurin series, this is going to be the sum from n equals 0 to infinity of the nth derivative at 0 over n factorial times z to the n here, because we're expanding about 0, so it's Maclaurin series. So this is n factorial, so this is exactly z to the n. Okay. Okay, so it works exactly as you would expect. So we could have found this expression using Taylor's theorem, just writing out its Maclaurin series. So this is, I'm just trying to drill into your head that however you come about finding these series. So we found this Maclaurin series accidentally before Taylor's theorem, right, through some algebra trickery, just noticing a property that allowed us to actually find this kind of formally, and then we saw, oh, actually what we did here was perfectly valid so long as z was in this open unit disk. So I can do that, and in any way that I find this, it doesn't matter. It has to be the same as the thing that comes out of Taylor's theorem. Okay. Now, what if I have a function that is 1 over 1 plus z? How would I find Maclaurin series for that? Well, notice that here I want to take this and I want to swap in minus z. So if I take this and swap in for z minus z, what happens? Well, what do I get? Well, if I have the modulus of z is strictly less than 1, then what do I get about the modulus of minus z? That's also strictly less than 1. Okay, so this condition still holds. And so I can just swap in minus z here, which means that I get the sum from n equals 0 to infinity of minus 1 to the n, z to the n. Okay, and of course this is valid for z in the open unit disk as before. Okay. All right. Similarly, what if the function in question is 1 over z? So now the swapping I'm doing for this original thing is I want to swap z and 1 minus z, right? Okay. So I want to replace z by 1 minus z. So if I replace this z with 1 minus z, I have 1 minus 1 minus z, which is just z. Okay, so here, going from, notice that 1 over 1 minus z, right, is equal to 1 over 1 minus 1 minus z, so this is 1 over z. So how can I do this? I can actually do this variable swap in the Maclaurin series, for instance. Okay, so this is the sum, right, from n equals 0 to infinity of minus 1 to the n times z minus 1 if I swap the order here, right? So if I, sorry, I'm actually using this. The minus 1 to the n doesn't come. I'm not using this series expansion at all. I'm using this one, but I'm swapping this order from 1 minus z to z minus 1, so I have a minus sign that shows up, and that's where the minus 1 to the n comes from. And the reason I'm writing it like this, the reason I'm swapping the order is because I want to write this as a Taylor series, right? And this is true for z minus 1, this thing I've swapped in, is that modulus is less than 1. Okay, so now this is actually a Taylor series about z naught equals 1, right? Now you might say, wait, right? You went from a Taylor series about z naught equals 0, that is a Maclaurin series, to, for this function, you wrote a Taylor series expansion about z naught equals 1. Why did you do that? Why didn't you write a Maclaurin series for this thing? This thing doesn't have a Maclaurin series expansion, right? Because this thing is not analytic at 0, right? Okay, that thing is not analytic at 0, and so doesn't have a Maclaurin series expansion. Okay. But it does have a Taylor series expansion about another point. Okay. All right, one more, and this is going to tell us exactly where we're headed here, right? Because notice this thing does not have Taylor series expansion about z naught equals 0. And so even for a function, right, that is analytic, everywhere else, right, away from 0, what if you want some kind of series representation for a function at a point where it's not analytic? Right? What do you do? Well, here's a more extreme example. Okay. All right. Let f of x, or sorry, let f of z be equal to 1 plus 2z squared over z cubed plus z to the 5th. Okay. Let's simplify this a little bit, or let's rewrite it in another way. Okay, so let's rewrite this slightly. This is, I can rewrite this numerator as, so first of all, I can factor out a z cubed from the denominator, so this is 1 over z cubed times 2 times 1 plus z squared minus 1. Okay, this is just a fancy way of rewriting this, so you can just check. This would be 2 plus 2z squared minus 1, so this would be 1 plus 2z squared, so that's fine. Why would I rewrite it like this? Because once I factor this z cubed out, what I get down here is 1 plus z squared. Okay, and that's why I wanted to write it like that. And so now, dividing through each term in the numerator here by 1 plus z squared, this is 1 over z cubed times 2 minus 1 over 1 plus z squared. Now this is going to let us see how things work a little bit better. Okay, so note, f of z has no Maclaurin series. Expansion because it's not analytic at 0, right? It's not analytic at z equals 0. Okay. But recall, one over 1 plus z is this, right? So what is 1 over 1 plus z squared? 1 over 1 plus z squared, I can get this expansion from the expansion for 1 over 1 plus z by putting in z here instead. Right, so, or sorry, z squared here instead. So if I put z squared here instead, this is the sum from n equals 0 to infinity of minus 1 to the n, z to the 2n, right? And so this is going to be 1 minus z squared plus z to the 4th minus z to the 6th, and so on. Okay. And that is going to hold if modulus of z is less than 1, right? Same condition. Okay. Okay, and so using this expansion in the way that I've written this function here, what does this mean? It means that thus f of z is 1 over z cubed times 2, right, minus this thing here. So now I'm going to swap the signs. So this is 2 minus 1 plus z squared minus z to the 4th plus z to the 6th minus z to the 8th, and so on. Right? Okay. And so multiplying through here, I get that this is, so 2 minus 1 is just 1, so this is 1 over z cubed plus, this is z squared over z cubed, so this is plus 1 over z, okay, minus z is the 4th over z, so that's minus z, okay, and then plus z cubed, right, minus z to the 5th, and so on. Okay. Rewriting this slightly, this is z to the minus 3 plus z to the minus 1 minus z to the 1st, if you like, plus z cubed minus z to the 5th, and so on. So, this thing has no Maclaurin series expansion, okay? But what we did write is an expansion for f about 0 that is kind of like a power series, but there's these negative powers. So I have negative powers here of z. This is what we're calling negative powers. Okay. So it's like a power series, except there's some negative powers here, right? So this is a power series with some negative powers. Now, I'm not pretending like that's not a big deal, because obviously this is a bigger deal. Once you have negative powers, for instance, right, this thing is clearly, it's not analytic at 0 because of these negative powers. You can just see that. So it has no Maclaurin series expansion about 0, but it has an expansion like this as a power series with some negative powers. It turns out we're going to have a special term for this, and so what we can say is the following for this example. So the point of this example f of z has no Maclaurin, which is just a type of Taylor series expansion. So Taylor series expansion about z naught equals 0, but it does have a Laurent series expansion about z equals 0, or z naught equals 0. So this Laurent series is exactly what we are going to call these power series with some negative powers. Okay. And so the notion of a Laurent series is going to give us a way of having an almost power series expansion for functions that are a little bit less nice, right? That are a little bit more general than ones we require to be analytic at some point. Okay. And so how does this work? So thus we want to kind of lay the foundation of the notion of Laurent series. In order to do this, I have to state what's called Laurent's theorem, which is really, really important here. So I need more room for this one. Let me get more sheets. Okay. So I have the following theorem. And this is called Laurent's theorem. Okay. Suppose, before I write more, I'm going to draw a picture of the thing that's going on here, right? So in that last example, we had the issue of the function in question was not analytic at some point, right? So for instance, it wasn't analytic at 0, and so it didn't have a Maclaurin series expansion about 0. The idea here is, suppose that I do have this point that is a problem point. So f is, say, not analytic at z naught. Now, the way that this works is, let's say f of z is not analytic at z naught. Then by Taylor's theorem, right? I mean I can't apply Taylor's theorem, right? So I can't apply Taylor's theorem. Okay, at least at z naught. Okay, but I want to try to find a series expansion for f of z at z naught anyway. Okay, so this is necessarily not going to be a power series, because if it was, it would have to be equal to Taylor's series, and Taylor's theorem would be fine. But here, I know that we'll say that f is not analytic at z naught. Okay, so I want to find a series expansion for f of z at z naught. Of course, this thing is not going to be analytic at z naught, but I want it to be analytic on a neighborhood around z naught where I have excised some bad points, right? So the thing is if I consider an open neighborhood of z naught like this, I know that my function is not analytic at z naught, but what if I excise some disk around z naught such that my function is analytic on this annulus around z naught? Okay, so it's not analytic at z naught, but if I excise some neighborhood of z naught from this larger neighborhood of z naught, what I'm left with is this annular region, and if my f is analytic on this annular region, right, I proceed trying to come up with a series expansion where I can actually do something here. I can actually write this f as some kind of series expansion. It's not going to be a power series. So how can I do this? Well, this is where Laurent's theorem comes in. So this is the picture. Okay, this is the picture. So then suppose that f is analytic. Suppose f of z is analytic throughout the annular domain given to me by the modulus of z minus z naught is strictly between two radii, r sub 1 and r sub 2. So centered, this is an annular domain centered at z naught. Okay. And let C be any positively oriented simple closed contour around z naught lying in that annular region. Okay, so again, bringing back our picture. here's C, right? There's my positively oriented simple closed contour C. Okay. Then, at each point in the domain, f of z has the series representation given as the following. So f of z is the sum from n equals 0 to infinity of a sub n times z minus z naught to the n Okay, plus a sum from n equals 1 to infinity of b sub n over z minus z naught to the n. And this is true for all z on this annular region. Okay, where I can actually compute these coefficients, and I can compute these coefficients using contour integrals where a sub n is 1 over 2 pi I times the contour integral of f of z dz over z minus z naught to the n plus first. Okay, and b sub n is 1 over 2 pi I contour integral of f of z over z minus z naught to the minus n plus 1 dz. Okay. Okay. This way of writing f of z is called the Laurent series expansion. So such a series expansion, such a series is called a Laurent series. Okay. All right. Now, we actually have a more compact way of writing this. So, note, we can write this in a little more compact form. If we replace n by minus n in the second sum, so let's bring it back. So if we replace this n here by minus n, we can actually combine these series. Okay, so b to the minus n here is going to be it's going to be 1 over 2 pi I times the contour integral of f of z dz over z minus z naught to the n plus 1. Okay, and the series, that second sum, is going to become the sum from n equals minus infinity to minus 1, okay, of b sub minus n over z. Sorry, this looks like b minus n. It's b sub minus n. So this is over z minus z naught to the minus n. Okay. Okay. Then we can write f of z as the sum from n equals minus infinity to minus 1 of b sub minus n times z minus z naught to the n, right, plus the sum from n equals 0 to infinity of a sub n times z minus z naught to the n. And I don't have to change those because those are positive n's for z in that annular region. Okay, but if I define, say, coefficient c sub n to be b sub minus n, when n is less than or equal to -1, and a sub n when n is greater than or equal to 0, then I get that f of z is the sum from n equals -infinity to infinity by combining these two of c sub n times z minus z naught to the n, right? Where, again, this is for z on this annular region. So here's a compact way of writing this Laurent series. Okay. And of course, I can compute these c sub n's in the same way from those contour integrals as 1 over 2 pi I times contour integral of f of z dz over z minus z naught to the n plus 1. So for this reason, because there's not cases here, sometimes writing it in this way is preferred. Okay, where n, of course, is 0 or plus minus 1, plus minus 2. It's an integer, right? And so this is another way of writing the Laurent series expansion for f. And so, ultimately, right, what is the point here? The point is that while we couldn't write a Taylor series or a Maclaurin series expansion for the types of functions we're interested in, say about a particular point. So, for instance, that last example we did, right? We couldn't actually come up with a power series expansion for the function around 0. Okay, but we can come up with a Laurent series expansion about that point that is analytic on some annular region. Okay, so it's still very much not analytic at that point, but it's analytic on some annular region of that point, and it gives us a way of expressing that function as a type of series, right? It's not a power series anymore because there's those negative powers, okay? But a lot of the same strengths or benefits of writing it or of having a Taylor series expansion kind of follow through here because we still have a series expansion, a nice way of writing this. And this is going to become extremely useful to us going forward. So this is how we hope to get to this very last fact that we want to talk about. That's kind of our most important thing that we want to get to, which is the residue theorem. So that is where we are headed, full speed ahead, trying to get there and apply all these goodies to those computations. So anyway, that's what's going on. So we will start here tomorrow. We'll finish everything we need about Laurent series, and I'll kind of finish up the niceness about various power series stuff that I'll relegate the details kind of to, if you want to go through them, I'll just state the results. And then we will be headed on to discussing singularities and isolated singular points specifically. We should get there by the end of lecture tomorrow, hopefully. So anyway, this is where we're headed. So I will see you all tomorrow.